Good morning, everyone. Thanks for joining us on this webinar on using OCS high-speed counter outputs. If you have any questions at any point, you can just put them in and we'll get to them at the end.
Hello and welcome to today's webinar. Today we will have a look at using OCS high-speed counter outputs. Let's look at our agenda for today. We are going to start off today's topic by talking about different applications for high-speed outputs. We are going to describe what are the high-speed output functions that are available by the product line. We will go through the 4 major product lines here, and there will be demonstrations throughout, and we will finish with a Q&A session. Let's start by talking about the different applications in which you can use high-speed outputs. You can use high-speed outputs for PWM. What would PWM stand for? PWM stands for pulse width modulation. And there are some devices, drives as an example, which will take a PWM signal and use it to control speed. For instance, the duty cycle of 0%, in other words, the signal being completely off, which will cause the drive to be a minimum speed, or let's say 0 speed. Whereas maximum speed will be when the signals coming to it is at 100% duty cycle. So if it is a 1K signal, 1000 Hz, and if the duty cycle is at 0, it is off. The drive will go minimum speed if the duty cycle is at 100%. In other words, continuously on the drive will be maximum speed, and then in between, for instance, 50% on and 50% off. For that duty cycle of a 1K signal, it will be at 50% speed. So that is the PWM style output control, or the output that is from the OCS. The input to drive, for instance, is going to be used to control speed. In this example, very similar example of frequency, but this time instead of the duty cycle being the key to controlling minimum or maximum speed for the specific frequency is used. The drive that we are controlling through our frequency signal is measuring the frequency of the signal to determine what speed it should be running at. So 1000 Hz corresponds to a maximum speed and 0 Hz corresponds to a minimum speed, and therefore it measures the frequency of the signal. The OCS is sending it and determines what speed it should be running on based on that. So at 500 Hz, for instance, in this example, it would be running at 50% speed. What are some examples of a programmable limit switch applications? Well, it could be that you want to turn on an actuator on at a very precise machine position that is independent of the logic scan. In other words, so regardless of where the PLC or the Horner OCS is, effectively you want to turn on output on at a very precise location. For example, you have a stamp and press which has a 0 to 360 degrees machine cycle, and let's say you want to energize an extractor at exactly 200 degrees of that cycle. So there will be an encoder or some other position sensors that will be connected to the high-speed counter circuitry of the OCS in our case. And then we want to make sure that the output fires precisely at the right spot so that the extractor can go grab the part while the press is open and available for it, not at any other time, because then you could have a big crash. So these are the typical high-speed output applications that we will be talking about in today's presentation. Let's talk about functionality on each product line. Now from this chart, it makes it look like OCS product line has precisely the same functionality. Well, they all support the basics of PWM outputs and frequency outputs and programmable limit switch and CAM type outputs. However, there are some variations from series to series in terms of precisely how that is accomplished. If the functionality is similar by series, but there are some significant difference, then how do you navigate that? Well, the key is you start with the user's manual. So you need the user's manual for a particular OCS controller that you are using. And in that user's manual, you will find the section. If you look at the table of contents, you will find a section that details the high-speed I/O, both inputs and outputs. So that is the section of the user's manual that you are interested in. And within that section, you will find a series of tables that describe the memory map that maps the real I/O registers to the specific functions that are the key to control your high-speed outputs. So that is what we are looking at. The user's manual is the key because the memory map does vary somewhat by the product. Some products like the Prime and Canvas have a very similar memory map. Some products like the Micro OCS have a different memory map. So again, The individual memory map is the key. Now let's start with the programmable limit switch, or the CAM mode, where we are firing a high-speed output based on a high-speed counter position. That is effectively what we are doing here. So the high-speed counter might be set up for a quadrature encoder. It is in the totalization mode, where it is just counting pulses from a sensor, and based on a particular position or a particular value of the high-speed counter accumulator, we are going to fire an output independent of that logic scan. So we do not have to be at the bottom of the logic scan or to fire that input. We can do it at any time because the high-speed circuitry on the OCS, not the logic or the scan engine of the OCS, is controlling that output. Now when we say firing an output based on a high-speed counter accumulator, what it means is that you could be turning that output on, you could be turning that output off, or you could be toggling that output to that opposite state. When you have a match condition where you have the particular position that you want to fire that output when that matches the accumulator. So that is the keys. In other words, finding out all these different register maps are, what all the key registers are for making all this happen, the micro OCS as well as the XLE and the XLT, in addition to being able to turn an output on or off or toggle it when it matches the accumulator. It also sends a pulse output on a match, meaning it can turn the output on for a specific amount of time. Let's take a look at an example register map. So what we have done here is we have pulled the tables from, in this case, an Excel Prime manual. These are the key register locations for an Excel Prime, and also applies to Canvas as well. But you should double check the Canvas manual just to be sure. The match registers, these are AQ registers, and they are going to be double integer in every case, where we are setting those AQ values the way we want them in logic, so that those are the specific counts for our high-speed counter accumulator, where we are going to fire that output, and we have two match registers we can use. So the output will fire when either match 1 or match 2 is matched. So if you have got one location you care about, then maybe you should use match 1. If you have got 2 that you care about, you can use match 1 and 2 if there is more than that. There are ways to manipulate those two registers so that you can have multiple locations, turning them on and off as long as things are not happening too fast. You can then set match 1 and match 2 dynamically in your program and still make sure that they are set to the appropriate value so that they are firing at the appropriate time. You have got up to 2 match registers you can use. As you can see here, you are going to find the user's manual in the specific location where those real-world AQS are assigned. So other than the match registers, what else matters for the program limit switch in CAM mode? Well, output reset bits. These are individual Boolean bits that you will turn in your logic program to reset the high-speed output. For instance, you would typically use this if the high-speed output was turned on. For instance, when we hit a match of a value, in other words, the match register matched the accumulator of the high-speed counter, then it would fire the output. After that output fires, you may want to reset that and turn it off again, so it is ready to fire again. So you would use the output reset bit for your counter to make that happen. So that is what those are for, and you have 1 per counter. Now what else is important? Well, we want to know the state of the high-speed output at all times. Even though our logic is not controlling the high-speed output, the high-speed circuitry and the OCS is controlling the output. So if we want to know the state of that output, the high-speed output, then we are going to need to monitor that somehow. We're going to do that through a %i bit. So there is a %i 1603 in the case of Excel Prime and Canvas, which you monitor to tell you high-speed output number is 1 is on. And then there is another one, I1607. That tells you if high-speed output 2 is on. And of course, you need to look at the specific user manual to make sure that those address registers match what you need. So that is the important registers that we need to have for program limits. Switching CAM mode, now let's turn our attention to PWM and frequency output mode. So in these two modes, we are going to manipulate some registers in the OCS to cause the high-speed output to be set at a frequency and the duty cycle that we want at any given time. Let's take a look at those key registers. This happens to be the chart from the user's manual for the Excel Prime. And you can see in the XL prime we have a 32-bit value for duty cycle, and we have a 16-bit value for frequency. Now that is true of the XL prime and the canvas, but it is not the same in the micro OCS. So again, every manual is important, and effectively what you are going to do, at least in terms of the XL prime, is you are going to set your duty cycle based on 100% equals to 32,000 counts. So if you want 50% duty cycle, you would set your duty cycle register to a value of 16,000 and 25% duty cycle. You would set it to 8,000 because again, 100% duty cycle is a 32,000 count. And then to set the frequency of that output, that is just an integer in the case of an XL prime, and you have set that to typically a maximum of 10,000. Now why 10,000? This is because the outputs of the high-speed outputs that are built into XL prime series and the micro series products typically max out at 10k in terms of frequency, so setting it higher than 10k is not going to do anything for you. It is just going to be on all the time. So you're going to set the frequency register to a value between 0 and 10,000 Hz. For our demonstration, we are going to start by being Cscape 10.1 for the higher speed output type function. Most of the instructions are going to be in the hardware configuration, so let's go there now. We're using XL Prime 4 Model 6. With that Model 6 I/O 12 in and 12 out digital, 4 in and 2 out analog. So that is the model we are using. Let's go to the local I/O tab and hit the configure button and the module setup. And then we will start by taking a look at our configuration. So we are going to start in the digital input / high speed counter side of things. Now for our first example, we are going to be in the PWM or PLS mode, limit switch mode. So that means we are going to be firing output based on encoder position. So for our demonstration purposes, we have set up for counter number 1 a quadrature setup. So simulating a quadrature encoder using our I/O simulator. So this is what is happening on the high speed counter input side of things. And then there is one other thing we have to set up from an output standpoint here. In the HSC input configuration area, that is the match function. So that is what we will be using when we are firing input. We will hit an encoder position or a counting position if we use this match function. So what are the match functions that are available? Well, disable is by default, but if we are using it, there is an on mode, which means when we match a present target value, when our encoder input or our count input matches a present target value, we are going to turn on our high speed counter input, our high speed counter output. So that is on mode. And then we can turn it off again through an internal bit in the logic. In off mode, it works the exact opposite. In off mode, when we hit the present value, the output turns off, and then we can switch it back on again through an internal bit that we can turn on in our program. And then there is a toggle mode for match setting, and that is when we hit a match, we toggle the output to the opposite state. So if it is currently off and we hit a match value, we turn it on. If it is currently on, we hit a match value, we turn it off again. So those are the modes that are available for our demonstration. So we are using on mode. Now for the rest of the configuration, let's go to the digital output and the PWM configuration. We have got our first digital output Q1 set to be an HSC1 output. That is the match output. So that means that when we match the present value, that when we are going to manipulate the physical output, which is Q1. Now the other demonstration that we are doing is with Q2, and that is we are going to use in PWM mode. And PWM mode could mean either that we are going to set Q2 to a constant frequency and vary the duty cycle. That could be considered a PW type operation, or it could be a frequency mode as well, where we want to vary the frequency maybe on Q2 and we leave the duty cycle always at 50% and we vary the frequency on Q2, that physical output. So that is what we are demonstrating for the second high speed output. Now let's take a look at things on the bench. Let's start with our CAM and programmable limit switch demo here. We have got our I/O simulator connected to our Model 6 XL4 Prime, and on the first screen here we are demonstrating the CAM and the programmable limit switch functionality, where our high speed output turns on based on the encoder position. So right now we are set up so that we are going to turn on that output to a count of 200, and then we are also going to turn on the output to a count of 300, and in between we are going to manually turn the output off in between those two particular locations. So that is the mode we are using here, where the match is set to on mode, and then we manually turn it off. So let's demonstrate this here. We will turn our encoder. You should see the encoder position counting up as you see there. Now when we get to 200, you should see the output turn on both on the screen and here with the I/O simulator, and we can see that the output is on. Now it is Q1 over here, but what we look at on the screen here is a special I bit for high speed output number 1. It is %I1603. Now if the encoder continues to count up, we can manually turn a bit on. That will clear the output. We are turned off using Q1606, which is a bit that we toggle on, and then off again to reset high speed output number 1. And as the encoder marches up towards 300, when we get to 300, you should see it turn on. Now let's take a look at our PWM and frequency output mode. And for this, in the configuration output number 2, this is the one here, output number 2 Q2, that we are going to use as either the frequency output or the PWM output. Let's set up something with, let's say, a 50% duty cycle. Our duty cycle register here is based on a 32,000 bit count. So if we want a 50% duty cycle, then we will set that to 16,000, and then we will set our frequency typically anywhere between 0 and 10,000 Hz. The standard output that are used with almost every OCS are good for about 10,000 Hz. So let's say we are going to set it to 5K. So this is a 5 Hz signal with a 50% duty cycle. Or we want to change that to 1 Hz. You can see now we have a 1 Hz signal with a 50% duty cycle. Now let's say we want a 25% duty cycle. Then we should change this down to 8,000, because 32,000 equals 100% duty cycle, so 8,000 would equal to 25%. And you can see we are flashing at 1 Hz, but the output is only on 25% of the time. That concludes our webinar for today. Thank you so much for listening, and the Q&A session will begin shortly.
Okay, excuse me. So next week our webinar is on upgrading an application to Canvas. So if you have any in the pipeline of moving to Canvas, this may be a good one for you. The registration is up as usual. I don't see any questions in on this webinar, so I think failing that we can leave it here. Thank you all very much, and we'll see you next time.